All right, welcome back to part 4. So we've learned about the convolution and we practiced him on a problem here earlier. So just to show that we can do it, let's use the convolution, not partial fractions, to find the inverse Laplace transform of this guy, where this guy is 1 over the quantity s times s squared plus 25. Now you'll notice that this guy looks a lot like 1 over s times, or well, I could rewrite him as 1 over s times 1 over s squared plus 25, which is close to, but not exactly, somebody that we know, at least the second piece. The first piece, we know the inverse Laplace transform for 1 over s. That's easy. The inverse Laplace transform for 1 over s is 1, okay? The second guy, though, looks fairly familiar. He looks a lot like the sine of kt, except I'd need a 5 up here, because this is s squared plus 5 squared down here, because 25 is 5 squared. Okay, so since I don't have a 5 and I need one, let's times by 5 over 5. So we've now got, over here, we've got 1/5 times 5 over s squared plus 25. Okay, and we can do the inverse Laplace transform on that, getting 1/5 times the sine of 5t. So we could use our convolution theorem, which says that the inverse Laplace transform of capital F of s times capital G of s is equal to f of t convolute g of t. So this inverse Laplace transform then of the original problem, 1 over quantity s times s squared plus 25, is going to be worth 1 convolute 1/5 sine of 5t. Now remember in our previous page here that we said that you can do the convolution in either order, but whichever one we do, whoever's first gets the x input and whoever second gets the t minus x input. So if I look at it this way, that's going to put the t minus x inside the sine function, which is going to be a whole lot harder than if I do it the other way around, which is 1/5 sine of 5t convolute 1. Now this 1 is always 1, so it doesn't even matter if I put in t or x or t minus x. So I'm going to go that way so that it will make the integral easier for me. So we're going to then get equal to the integral of 0 to t of 1/5 sine of 5x. Okay, so there's our capital F of, or sorry, our f of t guy, times g of t minus x, but it doesn't matter because this function's a constant. He's always a 1 times dx. And so that's going to make this guy actually a whole lot easier than doing him by partial fractions. So we've got 1/5 the integral of sine of 5x dx from 0 to t. And the antiderivative of sine of 5x would be negative 1/5 cosine of 5x. And we're going to evaluate that from 0 to t, which would then be, let me factor this negative 1/5 all the way out front. So we've got negative 1/25 times the cosine of 5t minus the cosine of 5 times 0, which is 0. And we like 0 because the cosine of 0 is 1. So we would then get negative 1/25 times the cosine of 5t minus 1. Or if you wanted to, you could distribute that through negative 1/25 cosine of 5t plus 1/25. All right. Now, if we wanted to do this partial fraction way, we would have had to first start with 1 over s times s squared plus 25. And would have had to break them down as a over s plus bs plus c all over our s squared plus 25, and gone from that way. So hopefully you'll see that the convolution can save us some work. So he's a good tool to have in your tool belt. All right. So we have some interesting properties, and one of them is that if I have a Laplace transform, so he's piecewise, f of t is piecewise continuous and exponential order, then if Laplace transform of f of t is capital F of s, then the Laplace transform of negative t times f of t is equal to capital F prime of s. Now sometimes, because Laplace transform is linear, they will multiply both sides by a -1 and say that the Laplace transform of t times f of t is equal to negative f prime of s. So they multiply both sides by a negative here. Okay, and occasionally we'll even basically solve this for f of t. Okay, and then iterate that property to get this guy, and you'll see that that actually is on our handy dandy table of Laplace transforms. So here's our convolution, here's that guy, and here's the iteration of him. Cool. All right, so let's use this guy to help us find the Laplace transform for f of t, where f of t is t times cosine of t. Okay, so let's look at this and remember that the Laplace transform of t times, and I'm going to introduce another letter, g of t is equal to negative g prime of s. So that I can make it fit, I'm going to, if f of t is t times cosine of t, I'm going to call the g of t part just the cosine of t. Why would I want to do that? Because I need to find g of s, being the Laplace transform for little g of t, but we know the Laplace transform for cosine of t. We've seen him time and time again. So that would be, in this case, equal to s over s squared plus 1. Okay, so to get the Laplace transform of t times little g of t, what we need to do is take the Laplace transform of this piece, okay, which is s over s squared plus 1. We need to make him negative, and we need to do the derivative of that. So we're going to do the negative derivative of s over s squared plus 1. So I'll put a prime there to do the derivative. And so to do that, we need the quotient rule. The quotient rule is going to tell us, let's do the low d high. So s squared plus 1 times the derivative of the top, which is 1, minus high d low, all over low squared. Okay, which would give me s squared plus 1 minus 2s squared, which would be a negative s squared plus 1, but then we've got to negate all that, so we would get s squared minus 1 over s squared plus 1 quantity squared.